I'll try to start a series of solving some competitive programming problems. And the idea is just to take some problem per video and read it with you, and then think about the solution, give the solution, and maybe code it if it's not too long or if it's not too hard, just in order to make the video not too long. So I'll do this series in English because it's one of the things that I want to practice. And I think that is it. So for the first video, I will try to do some problem from a contest from AtCoder, which is AtCoder Beginner Contest 161. And I'll try to solve the problem F. So let's go. So this problem is called division or subtraction. And the idea here is that we'll be given a positive integer n, and then we will choose some integer k, which is between 2 and n, and then we'll do some operations with this integer, with the integer n. We'll repeat some operation until n becomes less than k. So the operations that we'll do are the following. So if the current value of n is a multiple of k, or if k divides n, then we replace n with n divided by k, and otherwise we will replace n with n minus k. So every time we replace n, then checks whether k divides n. If so, we divide n by k. Otherwise, we replace n with n minus k. So we'll keep doing that until n becomes less than k. And the problem asks us to tell how many choices of k will n become 1 in the end. So after we do these operations and eventually the choice chosen k becomes less than n, how many of those k's will have make the any value be 1? So let's see some examples here. So in this case we have 6 as the value n, and the answer is 3 because we have 3 possible choices of k, and the choices are k equals to 2, k equals to 5, and k equals to 6. So for example, if k is 2, then we start with 6, which is the given n, and then we see, oh, okay, so k, which is 2, divides 6, then we need to divide 6 by 2, and then we will arrive at 3. And okay, so now 3 is not a multiple of k, or k does not divide 3, so we need to subtract 2 from 3. So in this case, we will arrive at 1, and then this is a good k because the final value of n is 1. So for k equals to 5, we have that 6 is not a multiple of 5, so we can't divide it by k. So in this case, we subtract 5 from 6 and we arrive at 1. And in the case of k equals to 6, then we'll just divide this 6 by 6 and then we arrive at 1. So if you try all of the other possible cases, which are 3 and 4, then you see that these numbers do not arrive at 1. So for example, if we take the number 4, so if we take k as 4, then we start with n equals 6, then we see, oh, okay, so 6 is not a multiple of 4, so we need to subtract it with 4. Then we will arrive at 2. But 2 in this case is less than k, which is 4, and then we need to stop the operations, and this number is different from 1, so we don't count them on the answer. So if you do the same example, the same process for k equal 3, you see that you do not arrive at 1. So okay, so the other examples are quite big, so it's very hard to try them by hand, but I think it's enough to get what the problem asks. So okay, so we have this integer n, then we need to count how many k's between 2 and n will give us 1 in the end after we do these operations. So important thing is that n goes from 2 to up to 10 to the power of 12. So n is quite big here. Probably we can't solve it using some linear approach because by some rule of thumb, maybe an algorithm with complexity of 10 up to 10 to the power of 8 would be the maximum that we can do. So, okay, so how do we approach a problem like this? I think the first thing is trying to think what property does a k that makes an n become 1 in the end has. And I think this is a good goal to have, to discover properties that will make us arrive at 1. And to do this, to find this out, I think it's good to analyze how the operations are done. So so the operation is the following. If k divides n, then we replace n with n minus k. So if we try to think in more practical terms, when we say that k divides n, then it means that k is a divisor of n, and n is a multiple of k. And if we think about that on more practical terms, then we see that this is the same of saying that k is congruent to the value 0 mod, okay, I'm sorry, n is congruent to 0 mod k. This is the same as saying that n is a multiple of k and k is a divisor of n. Or in other words, when we divide n, we take the rest of n by the division of k, then this is equal 0. Okay, so by analyzing how these things are perceived in the practical way, then we can arrive at some observation that will help us. So okay, so given that, we can try to analyze both operations, both the division one and the subtraction one. So let's take the subtraction one and analyze it. So if we take the operation n minus k, okay, so let's start differently. So let's say that initially n is not congruent to 0 mod k. So it means that the initial value n is not multiple of k. And let's say so that n is congruent to some k, some x, I'm sorry, mod k with x greater than 0. Then this means that if we do the following operation, like n minus k, this is also congruent to x mod k. Why? Because when we are dealing with modular operations, it's certain that this number here, k, is also a multiple of itself. So the value of k here is 0. So n minus 0, which is congruent to x, is equal to x minus 0, which is congruent to x mod k. So the thing here is, if you take some number n, which is not a multiple of k initially, that is, it's congruent to x initially. Then if you keep subtracting it by k, it will never become a multiple of k, because the rest that will always arrive is x. So if you keep subtracting it by k, then we will keep arriving at x. So it means that if for a given n and a given k, if the initial value of n is not a multiple of k, then it will never become with these operations, because initially we won't be able to do this operation because we need these conditions to be true, and by definition it's not. And then the only option we have is to do this operation. But we have seen that with this operation we cannot arrive at some n at some point that will be a multiple of k. So we will never be able to do this operation. Okay? So it means that if n in the start is not a multiple of k, it will never become 1. And there is the other case that n starts as a multiple of k. So initially you have that n equals mod k. And then what we'll do is basically set n as n divided by k. And then we'll check again, oh, for this guy here, is it a multiple of k? If so, then we'll turn this into n k squared, and so on, until we arrive at some value, let's call it y, that is not, that's either less than k, and then we stop the operation, or it's not a multiple of k. So if we arrive at this situation, then we have the same situation here, that n is not a multiple of k, and then we will never be able again to make it a multiple of k. So for this value here, we just make it y minus k, then y minus 2k, and so on. So with these observations, we can see that there are only two cases. Or if you analyze in some way, it's just one case, but let's say that there are two cases. So first case is n is not a multiple of k initially. So in this case, we will only do n minus k operations until the end. So this is case 1. So case 2 is n is a multiple of k. And with that, we'll do sum n over k ops. And then, if after these operations, the remaining value is greater than or equal k, we'll do sum n minus k ops in this order. Okay, so there are just two cases. Or we do always n minus k operations, or we do some initial n divided by k operations until we arrive at a value that's not a multiple of k anymore. And after that, we just do n minus k operations. So, okay, so let's try to count how many of these of k's are in this case here. Okay, so we want to find, okay, so I'll just erase here just to make it simple. So okay, so first case, we want to find some k such that we'll do the operations n from n to n minus k to n minus 2k and so on until some n minus x multiplied with k, which needs to be equal to 1. Okay, so this is what we want to do, and we need to think which case will give us this property. So which case have this property that will make us arrive at 1, and by that we can think in the other side. So we can think in the reverse way. So we start with 1, and then we go to 1 plus k, and then we go to 1 plus 2k, and so on. And after that, we need to arrive at n. So if you analyze all the numbers between this sequence, we'll see that all of them has the pattern 1 plus some number multiplied by k, so they have the pattern 1 plus x versus multiplied with k. And this pattern will give us a number which has the rest of the division equals to 1 mod k. Because here k is 0, and this will make this whole value here equals to 0. So if that's true, if all of these values have rest 1 mod k, then this is the same as saying that this is the same as starting as at n minus 1 and then go to, okay, so let me, I think I have complicated things, but we need to count how many numbers are there between let me see, I got confused. So let me explain in another way. So we can see this problem in another way. So instead of going from n to n minus k and to n minus 2k and to 1, we can start from n minus 1 and then go to n minus 1 minus k until n minus 1 minus 2k, and eventually we will get to 0, because just what we have made here is put some minus 1 in every operation, and this is similar to this whole chain of operations here, just with every value shifted to 1. So the values that will make us start from n minus, the values of k, which will make us start from n minus 1 and arrive at 0, are the values of k which are divisors of n minus 1, because if they are not divisors of n minus 1, then, because after all what we'll do here is have a value here that is of the form n minus 1 minus xk, and this value here needs to be equals to n minus 1 to this result be equals to 0. So this guy here is surely a multiple, a divisor of n minus 1 because it eventually, this product reached n minus 1. So for the first case, supposing, given that this chain of operations is similar to this chain of operations, we just need to count how many divisors n minus 1 has. So for the second case, what we need to do, we can actually count this case by hand, let's say like that. So in this case here, the precondition so that we are in this case is that n is initially a multiple of k, or in other words, k is a divisor of n. Given that, let's say that we have processed all divisors of n. So let's say that we have a list of divisors. We have divisor A, then B, then C, then D, and so on. This is case 2. So what we need to do is to check to get these divisors, then we will just simulate this case by hand. So we get a divisor A, and then we start with n, then we go to n over A, then we divide by A again if it's possible. So we have 2A until it's not possible anymore. So until this value is not, the current value is not divisible by A anymore. And then we will arrive at some value y. And then the operations that we could do from here is just to subtract A from y until we arrive at some value. So when we are in this case, basically we will arrive at a value equals to 1 if y has modulus 1 mod a. So if y has modulus 1 mod a, then this means that this initial divisor, which is a, will make us arrive at some value 1. Because let's say that we will continue the operation, so we'll do y minus a, and then y minus 2a, and so on to 1. For this to happen, as we have already seen, if we do y minus a, then this a here is equal to 0 mod a, I'm sorry. So y minus a is equals to 0 mod a. So the only way to arrive at 1 is if y is 1 here, or in other words, if the rest of the division of y by a is 1. Okay, so for this case, we have, for case 1, what we need to do is, again, calculate the number of divisors of n1, n minus 1, and we can do the calculating of the divisors on complexity O square root of n. And here we also need to calculate the divisors of n, so we need to enumerate them. and that will have the complexity O, the square root of n. And for each divisor, we need to divide n by the divisor itself until it becomes not a multiple of the divisor itself. So there is some extra processing here. So the processing here will be, let me think. Will be something close to the log of n, because the worst case is like having some, let's say that n is like 2 to the power of 16, so one possible divisor is 2, and then we need to divide this guy here 16 times, which is basically the log of n. So overall we have a complexity which is square root of n multiplied by log n, which is the worst case. So in this case, n is close to 10 to the power of 12. So this operation here will be like 10 to the 6, and this here will be like 40. So in the end, we'll have like 10 to the power of 6 multiplied with something like 40, and which is 4 multiplied with 10 to the power of 7, which is pretty okay. Yeah, so I think it's that. So we basically need to find the divisor of n minus 1 and count them. And here we need to find the divisors, divide them by k, by the divisor itself until it's possible. And then we see that if the result has REST1 modulus the divisor. So I'll try to code the solution here. So the first thing is to read n, which is the only input. So here we need to use the long type because n can goes up to 12 to the power of 10 to the power of 12, and int type goes up to something close to 2 to the power of 9, 2 to the times 10 to the 9. So okay, so the first thing we need to do is create a function to calculate the divisors of some number, because this is used in both cases. So we can do like something like that. That function will receive some number n, some number x, and it will return us a list of divisors. So if this list is called d, then we need to return g. And then for calculating the divisor of some number, we can use a strategy that will go until the square root of the number. So the stopping condition of this for tells us the following: oh, if the square of I is greater than x, then stop. So it means that we will only go to the square root of x, and we will check whether I is a divisor of x. So if so, then I is a divisor of x, of course. So we put I on the vector, and when we find a divisor of some number, then this divisor has some other divisor which is apart. So for example, let's say that I is a divisor of x in this case. So it means that if we divide x by a, then we'll have another value which is equal to I. And this value is also a divisor of x, because if we were to multiply it by I, then we would have it equals to x. So if we have like, okay, so in this case, we could just put this other guy in the divisor array 2. But there is some trick case. So let's say that we have x equals to 16, then we have I equals to 4. In this case, we have that I is equals to x over I, because this will happen when x is a perfect square. So when we reach the square root of x, then we'll be putting the same number 2 times on the array, but we don't want that. So in this case, we can just check if the square of I is different from x, and if so, we put this guy also in the array. So okay, so this should be the function that calculates the divisor of a number. So now we can just calculate the first case, which basically calculating the number of divisors that n minus 1 has. So case 1, we'll have like us, we'll sum the count of divisors of, I don't remember if it's size, I think it's size of the array, that the number of divisors of n minus 1 basically. So just checking whether it's okay. So for case 2, we need to find all divisors of n, and then we will iterate over all of them. Okay, so in this case here, this function divisors will return us the number of divisors that so this function will return all of the divisors of n. In this case, 1 will be also returned here, but we will want to count only cases that are from 2 to n. So if e is equal to 1, we just continue. We don't want to count e as 1. So in this case here, we also need to subtract 1, because if 1 is present in this vector, we also want to remove it from the count. So 1 will be in only one of the 2 cases. No, actually it will be on both, but we don't want to count them on both. So okay, so in this case, basically we will just keep dividing the number, the number n, which is, I made a copy just to not change the original value, and we just keep it dividing it by the current divisor, which is this step here. We will keep doing this until we can't do anymore, and then we just check whether this final value modulus a is equal to 1, and if so, we increase the answer, and that should be the final answer. So if we check here, let's say if everything is okay, so okay, I think things are okay. You can try some edge cases, like 2 should be 1, because it will be okay when k is equal to 1. We can also try the largest case to see that we don't have some overflow or something like that. Seems okay. Yeah, I think it's okay. Let's submit it and check whether it passes the solution. So okay, it seems correct. So I think it was for some good use, this screen recording for you guys. And if you have some doubt, you can leave in the comments. I I hope to improve my speaking for the next videos. And I think it's that. Bye bye.